Hey students, I hope you're having a wonderful day. I know that your test is just around the corner, and no worries, we will learn about chemical bonds today and how it can help you to refresh back all of your studies regarding this topic. So to start, we have to know, we can start over from the beginning. So what is a chemical formula? So when elements combine to form compounds, a chemical reaction, it creates a new compound with properties that are different from original elements. So when a new compound is formed, it has a new chemical formula. So the chemical formula will tell you what elements a compound contains and the number of atoms of each element in that unit. For example, we have a table salt here, and we know that it's made of two elements, which is sodium and chlorine. So this is the chemical formula of salt. But no worries, we're gonna see more example after this. So how and why do atoms form compounds? So because of the electric forces between the electrons and protons, which are oppositely charged, atoms and molecules together, which cause compounds to form. But not all atoms can form compounds readily. Some elements, such as the noble gases in group 8, they have electrons they need. So their energy of outer level energy already filled and no longer require anything. So they are chemically stable. So how does an atom become chemically stable? So when an atom is not chemically stable, it must bond with another atom to become stable. To do this, an atom must gain or lose electrons to becoming an ion. So an ion is a charged particle because it has either more or fewer electrons than protons. So for example, a cation is an atom that has given away its electrons, so it has become positive. So we call this as cation or a positive ion. And the next one is anion. So the opposite of cation, this is an atom that has gained an electron in its outer energy level and now a negatively charged particles. So there are multiple types of chemical bonds. So today we're going to learn about two of them, which is ionic bond and covalent bond. But we're going to focus more on the covalent bond. Okay, so an ionic bond is a bond that occurs when a metal gives away its valence electron, meaning electron on its outermost shell, to become a cation, and a non-metal element gains a valence electron and becomes an ion. So ionic bonds is formed between a metal and a non-metal elements. So usually ionic bonds have high melting and boiling points and can conduct electricity due to its positively and negatively charged ions. So these are how the two ways to show an ionic bonding. The first one is the electron dot method. So you can see here that the sodium element here, atom here, donates one of its electron to chlorine. So chlorine needs another one electron to be stable, and sodium needs to let go of this one electron to be stable. So these two elements, they become ions and they attract to each other and form another compound. So this example here, for example, Emily and Sarah here. So Sarah is very cold and Emily said, okay, take my blanket away because I don't need it anymore. So in this case, Emily is donating her electron to Sarah. So it's donates electron there and they become close to each other. And now covalent bonds form between non-metals. So rather than donating electrons, covalent bonds that share electrons. So this is a resulting compound is referred to a molecule, for example, water, oxygen gas, nitrogen, hydrogen gas. So example here that both Emily and Sarah, they both need this blanket. So rather than giving one away to each other, they share the blanket, and this blanket that is being shared is what is pair of electrons here. For example, a chlorine gas here sharing one electron to each other, and they both have 8 outermost shell electrons. So they are stable, but they have to share the electrons. So electrons are not always shared equally between atoms in covalent bonds. So this is where a polar molecule happens because a polar molecule has a slightly positive and a slightly negative end. So a non-polar molecule, they have electrons that are shared equally. I'll show you an example on this. So a non-polar covalent bond, just now, they share the electrons equally, meaning that the electrons are being divided equally. You know, it's being divided very homogeneously. While the polycovalent bonds here, for example, Sarah is much colder than Emily is. So when they share a blanket, Sarah get more of the blanket. So in case that the electrons density is more towards Sarah rather than towards Emily, even though Emily still has that electron. So this is what we call a polar covalent bond, resulting in an electronegativity. So you see that the atoms that are more electronegative, for example, here hydrogen chloride, that chlorine is more electronegative, so the density of the electrons are moving more towards chlorine than hydrogen. Inversely, that hydrogen gas is electrons are shared very equally to these two atoms, and they have the electronegativity is balanced. So electronegativity is defined as the measure of an atom's ability to attract electrons. So how does and what does affect electronegativity? So this includes the number of protons in the nucleus, the distance from the nucleus, distance of electrons from the nucleus, and the amount of screening by the inner electrons. So and then we're going to introduce a dipole moment. So when a molecule has a dipole moment, meaning that it's a difference in charge, so an arrow pointing towards the more electronegative atom. So for example, HCl here, the electrons are moved towards the chlorine. So this is what we call a dipole moment, and this is what makes it a polar molecule. So how do we define whether a molecule is polar or not? So it depends on the dipole moments and also the molecular shape. See the example here for HCl, that the electrons are more dense on the chlorine side. So non-polar molecules. So non-polar molecules are molecules that are cancel out each other. Basically, they are dipole moments. This is the difference in electronegativity. They cancel out each other. You can see here that BF3, the dipole moment is going upward, outward, and backwards in the same balanced way. So these dipole moments, they cancel out each other, and it becomes a non-polar molecules. Meanwhile, polar molecules, they have a dead dipole moment. So these electrons here is moving, for example, here, water here, that the electrons are more electronegative towards oxygen atom here. So the dipole moment moving toward upwards. So this one way of dipole moment, it creates a polar molecule. Therefore, most of polar molecules, they have asymmetrical shape, or what we call lone pairs or asymmetrical atoms. So you see here that it's moving to downwards. So it's a polar molecule. So these are some of the examples of polar bonds. So you can see here for the polar molecules, it moving always like one way, whether it's upward, downward, or right or left. But non-polar, they are balanced, meaning if one move upwards, one move outward and backward. So and here we see the non-polar here in four ways. So it's non-polar molecule. Now we talk about some properties of covalent bonds. So covalent bonds are poor conductors of heat and electricity because they are shared electrons rather than donating them. So they have much lower melting and boiling points, and they can exist in solid, liquids, or gases. So they have strong bonds between the atoms, but weak attraction between the molecules. So this is how you draw a covalent bond. So the element that is least represented, meaning the least amount in a molecule, for example, water here, oxygen is the least amount of atom, so it's represented in the middle. So only place the valence electron that will be shared between these two atoms, which is the hydrogen and oxygen here, and electrons are not being shared, must go to outside of the atom. So this is what we call the lone pairs. So and now we're going to move forward towards bond geometry. So geometry is the shape of the molecule. So how does one determine the shape of molecule? Okay, so we know some of the basics here. We're gonna go over right through this. So the first one is the molecular formula. This is when you see letters here, so for example CH4, this is what we call a formula. And then when you see a bond here, like a dash here, this is what we call a structural formula. So what we call a Lewis structure. But the shape is what we call a molecular shape. So this is how it looks like in three-dimensional shape. So this is how we determine how a molecule shape looks like. And this is where we induce our Vesper theory. So Vesper theory stands for valence, shell, electron, pair, repulsion theory. So this is how we determine how a molecule looks like. So some of example here is a molecular geometry. So if an atom here is balanced here, it's called a linear. If the atom has three domain electrons, meaning that it's connected to three different atoms here, we call it a trigonal planar. So this is most likely 120 degrees, and if it's connected to four, we call it a tetrahedral. So this is most of the time 109.5 degrees. And if there's a lone pairs, so this lone pairs here will repulse the bond here. It will repulse. Here's the lone pairs. It will repulse the bond here, a single bond made by this atom. So it will push it downward, so it becomes smaller, which is 107.3 degrees. And same goes here, there's two lone pairs here, and it will be repulse this bond here because this is an electron and the lone pairs are electrons. So when same charge see each other, they repel, they push toward each other. So it becomes 104.5 degrees. So this is what we call a bent trigonal pyramidal. So some of the example here for methane. So you see here that this is 109 because this is a tetrahedral, and this is ammonia because it has a lone pairs here. It will push down more and it become 107. And water has two lone pairs for its molecule, and it will push to this bond between oxygen and hydrogen here. It become 104.5 degrees Celsius degrees. So this is for ozone. It's also bent, even though it's a linear, but it bends because of the lone pairs. So these are some of the molecular shape and how can you remember. So if there's a three atoms, for example, here, water perhaps sometimes it's linear 180 degrees, but it will bend if there's a lone pairs. So it implies to the 5 atoms, 6 atoms, 7, and 4 atoms. So all of this, you only need to remember the name and remember if there's a lone pairs or not. So no worries, we have this table right here. So you can see this is the number of bonds and the number of lone pairs. And if you see there's a lone pairs, usually they will become bent. So they will repulse of this bond and they will become bent downwards. So these are some of the molecular shapes. So you can see there's many examples here. So this is the geometry covalent molecules of ABN and ABNEM. So basically, when you have a chemical formula here, and then we can see the type of formula here, and you can see the shape of, you can deduce the shape of the molecule by seeing how many electron pairs that they have, how many lone pairs that they have, and you see the ideal geometry here and the observed shape. So for example here, CDBR2, it is linear because it has shared shared electron pairs and there's no lone pairs. So it's not bent. So, but if you see there's an electron pairs here for a trigonal planar, so it become bent. So it will repulse the bond, the single bond or the double bond. So just refer to this table and you're able to see deduce the shape of the molecule. Now we're going to move towards atomic orbital. So what are orbitals of atoms? So electrons are found in a specific circular path around the nucleus. So it has a fixed energy called the energy level. So the energy sublevel correspond to an orbital of a different shape. So which describe where the electron is likely to be found. So what we can see here that orbit and atomic orbitals is where we are most likely can find electrons because the electron just don't simply circling around an atom. So it moves in a very particular way. So this is what we call in orbitals. So for example, this is our solar system here. Imagine the sun and the planets are all the protons, or basically the nucleus, protons and neutrons. So this asteroid belt here is where an orbital, what we call an orbital. So this is more likely where we can find asteroids. So the asteroid in this case in electrons. So even though we can find asteroids in other places in the solar system, but most likely you will find it in the asteroid belt. So this is a 90% probability for electron to be found in orbital. Now, so atomic orbitals are depends on the energy level and they are labeled by a quantum number principle. So this is example here for a level 1 and they have a one sub-level, we call it 1s or 1 orbital. So if it's a level 2, there's 2 sub-levels and we call it a 2s orbitals and 2p orbitals. So we're going to learn more about this. So it depends on the electrons of an atom. So we're going to learn about the shape of an orbital. So for the 1s orbital, it is a sphere. So when it tells you that electron in the orbital closest to the nucleus, so this is the smallest and the lowest energy one. So the S here tells you about the shape. So just to let you know that an orbital can hold up to 2 electrons. So if an atom have more electrons, they need to be scattered around a higher energy level of orbital. So we have a 2s orbital here, which is also sphere. And then we have the p orbitals. So for p orbitals, there are 3 different directions. The x-axis, y-axis, and the z-axis. So after the first energy level, there will be a second energy level, and this is where we found the 2p orbitals. And there's a d orbital. This is we found at the third energy level, and there's a 5 different directions. And in f orbitals, it is the fourth energy level, and there's a 7 directions. So you can see here in this diagram is where you can see a different energy level here. So we're going to see how we're going to calculate here. So the number of electrons in energy level, so we can determine that for each level, you see how many electrons. So this is for the first one is only the s orbital. For the second one, there's a 1s orbital and 1p orbital. So p orbitals can hold up to 6 electrons. So when 6 plus 2, it's 8. So in the 3, there's a d orbitals, and then there's 4 and 5, there's an f orbitals. So now we're going to learn about electron configuration. So it shows you in how we determine the electron, how the electron will fill up the orbital. So the number in the front is what we call an energy level, and the second is the sub-level. So this is the orbital S, P, D, and F. And the number 2 here is the number of electrons that is in that sub-level. So we must follow 3 rules for electron configuration. So the first one is the Aufbau principle. So it states that electrons occupy energy level with the lowest energy first. So what it means is to say that the one on the first on the early level have to be filled with electron first before we move up to the next level. And the second one is the Pauli exclusion principle. So if 2 electrons occupy the same energy level, they have to have an opposite spin, meaning that if one is spinning right, the other electrons must be spinning left. And the third one is the Hans rule. So electrons that occupy orbitals of the same energy, they have to have a maximum number of electrons with the same spin, meaning that if there's 3 electrons in a p orbital, it have to go in the same way. You have to fill up that the orbital first, then it goes to the opposite way. We're going to see an example for this. So the first one is boron. Boron has an atomic number of 5. 5 means it has 5 electrons. So how do we fill up this electron configuration based on this number? So you see that since you have 5 electrons, and the first level, it only have 1 s orbital. So for this s orbital can only fit 2 electrons. So we see here the arrows is 1 going upward, downward, and then we have another 3 electrons. Now for the second level, there's a 2s orbital and the 3p orbital, the 2p orbitals. So we know that s orbital can fit another 2 electrons, so we're going to fit another 2, and the p orbitals, they can fit into 6. So but since they only left 1, we only fill 1 of the p orbital here. So this is how the electron configuration looks like. So by following this. Now the last example is the calcium. So calcium has an atomic number of 20, so it has 20 electrons. So this is how we fill up the electron configuration by each level. As you see here that the 4s is being filled before the 3d, because the 4s has lower energy level than 3d. So basically, even though the 3d is on the third energy level, but by following the rules, we have to fill in the 4s first, because the atomic because of the sphere orbital has much lower energy, so it can be filled with the electron first. So this is what the electron configuration looks like. So that is all for today. I hope you revised well for your